This is a continuation of methods to protect ship hulls from mine and torpedo attack, some alternative approaches. In order to protect ship hulls against mine and torpedo attacks, it is necessary to have a crushable space. One possibility is to use hollow aluminum balls. The difficulty with that is it's actually difficult to manufacture a hollow aluminum ball. A much easier item to fabricate is a cup with a cap. The cups can be forged, the caps can be forged, and then they can be welded together. The cups would be grouped with the flat sides all in one direction, and then another group with the flat sides reversed. Those double layers would then be stacked out to whatever depth is necessary to achieve an adequate dissipation of energy from the explosions of torpedoes and mines. The effects are mostly viscoplastic. It goes from viscoelastic to viscoplastic. In either case, it takes time for the displacements for the stretching or the crushing. Plasticity is permanent deformation. The material, even after you unload it, remains in a permanently deformed shape. But in both viscoelastic and viscoplastic, there is time involved in the displacement, the amount of time it takes to displace, and that delays the shock wave from arriving at the protected hull. Another possibility is to use hollow tubes. The tubes can be square, they can be circular, or they can be hexagonal. The tubes would be attached in groups onto a plate, welded onto the plate. Another plate would be placed on top of them to make a sandwich. As many of the sandwich layers would be assembled as would be necessary to delay the explosion from arriving and damaging at the protected hull. The individual tubes would be designed to buckle under the loads, and again, buckling and going into viscoplasticity to delay the shock wave from arriving at the inner protected hull. There is a consideration of what design point for the crushable index and whether that provides adequate protection. If you try to find out what depth U.S. submarines operate at, you can find various numbers. Some people claim as much as 1,200 feet. At 1,200 feet, it's 80,000 pounds per square foot, about 600 pounds per square inch of pressure. Submarines have some reserve strength in the hull. You don't push the submarine hull to its ultimate strength point because there's too much danger of the hull imploding. There has to be some safety margin. With the explosion, you are clearly loading the hull past the 600-pound design point, but hopefully below the point that would cause failure. At the surface, the submarine hull has the additional 600 pounds per square inch that is used to absorb the pressure at depth. At depth, it's only that excess above 600 pounds. And the question is, though, the amount of time it takes for the material to deform. The viscoplastic movement of the material and how long it takes to deform is what protects the vessel rather than the ultimate strength of them. Achieving a density of less than 64 pounds per cubic foot is fairly obvious. Aluminum weighs 150 to 160 pounds per cubic foot. The stress of 600 pounds per square inch compares to an aluminum strength of over 20,000 pounds per square inch, and even much higher than that in better quality alloys. So you only need about 1/30th of an inch per inch, or 1/30th of the total area, which is about 5 pounds per cubic foot. Because it's in compression, it has to resist buckling, so it needs to have more material than that. But you don't want it to be too stiff that it's going to overload the hull from an explosive charge. It has to crumple, and that limits how much aluminum can be per square foot. So the question then becomes, how many layers do you need to resist an explosive charge to delay it and the pressure pulls the shock wave so that the inner hull is not damaged? The more layers you have, the more problems you get with just the overall shape of the submarine. This enables torpedoes to be mounted outside the submarine hull as the crushable material protects the submarine from its own torpedoes exploding. There is going to be some degree of flexing and bending of the hull under that loading from the explosion, but the hull will still have enough strength to resist those forces and survive and be able to continue to function and not be loaded past its ultimate strength limits.